All right. All right. Hello, everybody. Welcome back to Comp 3430 Operating Systems. I hope that you are all staying warm. I hope that you are all not just buried in snow yesterday. I'm glad to see that you're all here. It was kind of harrowing getting to campus today. It was real icy on the roads. It was not super pleasant. And I don't know about all of you, but I am pining really badly for summer right now. I'm at that part of winter where I am finished with winter and I would like summer to come back, please, so that I can do outside things and not just be stuck in my house all the time, or alternatively putting off shoveling the snow around my house. That feeling of I need to do this and just don't want to is just ever present at this time of year. I hope you're all doing okay. Today, we're going to keep on keeping on with file systems. Last class, we went through a pretty comprehensive example of the last two classes really. Here's an ext2 formatted file system. So how do I make a file with truncate? How do I format that file as an ext2 volume? So how do I use that makefs.ext2 program to put the bits down in this file that represent a file system? And then in a lot of detail, given the documentation for ext2, how do I find the contents of a file? So how do I actually find these structures? How do I find the inode table? How do I find the super block? How do I interpret the super block? How do I interpret the inode table? What do inodes actually look like in terms of hex bytes? And then eventually, how do I get to the contents of this file? So looking at directory entries, finding the directory entry that corresponds to the file that we're looking for, going back to the inode table to find that inode's direct block pointers, and then actually going to the direct block pointers. We did all that with hex dump on the command line. And I think I want to clarify a point here. I can't ask you to use hex dump on a test. To be really clear, I cannot ask you to use hex dump on a test. And I would never print out dozens of pages of hex and ask you to draw arrows and lines and stuff between things. That's not the purpose of that exercise that we went through. The purpose of the exercise that we went through is really, I'm going to give you documentation for a different file system. And I'm going to give you examples of that file system. And I want you to have the ability to take a look at that documentation and then use a tool like hexdump to find where stuff is in this thing. For the purpose of, you're going to have to do this for an assignment, actually write code to read the file system. So how can you use hexdump to get a sense of where you are right now? So the entire purpose of this whole hex dump with ext2 was very much just give you the tools to help yourself when you're doing this on your own time with a different file system. So I'm not going to test you on using hex dump. I'm not going to test you really that much on ext2 outside of what VSFS looks like in the textbook. That's the limit to what I really care about for that. I also had a question. I had an appointment with somebody yesterday. They were kind of feeling a little bit uncertain and nervous about the textbook readings, the level of depth to go into for the textbook readings. And they're specifically thinking about the chapter where it's describing read and open and stuff like that, all the different functions that you are interacting with when we're working with file systems. For that specific chapter, I want to be clear that I'm also not going to test you on any of that stuff. I don't care if you can call read or not on a test. You're going to do it all over the place in your assignment. This is a third-year course, and in third-year courses, at least for me, I'm talking about my own personal opinion here. I don't really represent the department necessarily in this, so you can't take this as a universal truth, but you've spent the last 2.5 years getting tested on programming. I'm almost certainly not going to test you on programming. I'm almost certainly not going to test you on programming. You'll get lots of programming stuff with the assignments. You're going to get a ton of programming stuff with the assignments. I'm almost certainly not going to ask you anything like that on the test. So please don't feel the need to spend the time like memorizing things like the argument order for read. I don't care about that. I'm not going to be asking you questions like that on the test. The kinds of questions that I might ask you on the test would be more of the form, given this code, read, open, and then read, describe to me the data structures that are being used in the file system to satisfy this call. So like, what do you have to actually take a look at to do an open? What do you have to actually take a look at in terms of data structures in the file system to satisfy a read? That's the sort of thing, and that's the sort of level that I'm going to be asking you questions about on tests for stuff like this. We will talk more about tests when we get closer to that point, but just to give you a sense of what I'm looking for specifically for that chapter. All right, okay, so we did all that hex dump stuff, and then we talked about how that's painfully tedious, and then we moved on to writing C code to do something very similar to that. Today, what I want to do is kind of the same thing. We're not going to be using hex dump at all, and I'm not going to be writing any C code. The purpose of today's lecture is going to be, I want to give you a high-level description of a file system format. I want to give you a visualization of that file system format to the point that you should be able to take this high-level visualization and the extensive documentation that we see, and you should be able to write code to implement something that will work with that file system. So that will involve you being able to describe how a specific file system is implemented, and then showing how common file operations are performed in terms of manipulating a file system's data structures. So we're going to take a tour of the different data structures that are in this file system, and similar to ext2, I'm expecting you to be able to say, like, these are the data structures that I would use when I'm trying to read a file. These are the data structures that I would use when I'm trying to change the contents of a file or create a new file or folder in this structure. That file system is exFAT. A lot of people I'm hearing are saying exFAT. I actually have no idea what the correct pronunciation of this is. I'm going to keep calling it exFAT, but you're very welcome to call it exFAT, and I'll make sure that I've got this this synonym name in my head when I'm talking to people. Let's take a look at this documentation, and then what we're going to do is switch to kind of drawing the structure of this thing out. So I put this link in the course content section for today's lecture. If you want to have this on your screen at the same time as I do, then you can kind of follow along with me. I think I said this last class, but I think it's worth repeating. I personally believe this document to be a very good document. It is comprehensive, it's to the point, it contains everything that you need, and it doesn't speak down to you as a reader in terms of like telling you about the file system itself. I think that this is a good document for that. I think it's well organized, and I think it's generally clear. I'd also like to note that Microsoft here has been responsive to corrections to this document. I've had students in the past tell me like there's something weird about this, and so I made a merge request to Microsoft, and they accepted the merge request for this documentation based on feedback I've received from students. So I believe that this is a good document, and they're willing to make changes to it when it's appropriate to make it clearer or to make it more valuable. Overall, really big high picture, exFAT is the successor to the FAT family of file systems. The very first FAT file system was something that, please don't quote me on the date here, but I think it was like 1979 was when the first FAT file system was written by none other than Bill Gates himself. I mean, I think he bought the code from somebody else, but Bill was actually involved in the development of this code and migrating it to Microsoft's disk operating system. But this is the successor to this, and it has a lot of the same kind of like big concepts that you'll find in these other FAT file systems. So when we're talking about exFAT today and taking a look at the overall structure of the whole file system and the concepts of the file system, a lot of what you're seeing here will translate to these other FAT file systems. So if you have some sense of what exFAT looks like, you're also then intuitively going to have some sense of how FAT32 works. The design goals for this, I think, are also pretty good to have up front, in that we're trying to learn a little bit about file systems and why they're designed in a certain way. So one of the first design goal here is retain the simplicity of the FAT file systems. These are bytes. Like when we're looking at this stuff, we're going to literally be looking at bytes and hex and dealing with binary files. But the most complicated data structure in this file system is a linked list. And we've been doing that really since, like, I don't think you started in 1010, but in your first year in 1020, you were definitely doing linked list structures. The linked list structure that we're going to see doesn't actually look like a linked list structure. It doesn't look like it at first, but we're going to see how it is a linked list structure. The thing that we're going to see that represents this linked list structure is the FAT, and the FAT itself is an array of numbers. It's just an array of numbers, but we're going to use that array of numbers to represent a linked list structure. Enabling very large files and storage devices. The FAT family of file systems, so FAT32 is the last one. This is limited to a 4 GB file size. That's the biggest file that you could put in that kind of file system. The exFAT system uses 64 bits, so FAT32 uses 32 bits to represent the possible size of a file. exFAT uses 64 bits, which is like terabytes now we're getting into in terms of the volume that we could have on a single file. And then incorporate extensibility for future innovation. We're going to see some of the stuff that's in here that represents like how it could be extended. I'm not going to dwell on that, though, because I don't think that that's important for what we need to know about for this file system. I'm going to keep scrolling down here, and I'm going to skip this part. This is kind of common on like documents that describe specifications, saying like, if you implement it, you must do this versus it's optional for you to do this. And then in practice, the word optional actually means that most implementations don't do it, because why bother? And then there's a full list of acronyms here. I think this is a good document. I really think this is a good document. This here, this is part 2. This is the volume structure. This is the very first thing that I want to take a look at here. The volume structure is the table that kind of represents the whole file system. This is a big table that represents all the different regions that you will find in that file system. So with VSFS, we had this nice diagram that says, here's where the superblock is, here's where the allocation structures are, here's where the inode table is, and here's where the data region is. This table is effectively the same thing, but what I want to do is I actually turned this table on its side, and I'd like to show you what this table looks like on its side in something that's a little bit more of a familiar approach, a familiar layout of this thing. The first thing that we find in exFAT is this thing that's called the main boot sector. I will share this diagram with you after class, so I'll put the PDF copy of this up on the course webpage so you don't have to take it all down if you don't want to. The main boot sector is synonymous with the superblock. These are the same concept. They mean the same thing. The main boot sector has metadata about this file system. It's going to have information for us like how big the volume is. It's going to have information for us like how big the clusters are. And I'll talk about the word cluster in just a second. And it has information like, here's the label of the volume. Sort of. We'll talk about that in just a second. The main takeaway here is that the main boot sector itself is, the main boot sector itself is equivalent to the superblock idea. These things are equivalent to each other. They mean the same thing. They're just different words to describe the same concept. The main boot sector is measured in a unit called a sector. We will talk about disks more later, but a universal truth for us is that a sector is 512 bytes in size. That is our current universal truth here. So that means that our main boot sector structure is exactly 512 bytes in size. It's not bigger than that, it's not smaller, it's exactly 512 bytes in size. I'm going to take a look at the main boot sector in a moment, but there's a bunch of other stuff that comes after this that is completely irrelevant to us, and so I'm not going to dwell on it. There's extended boot sectors, there's OEM params, and there's something called the boot checksum. It doesn't matter. We're never going to look at this in this class. It doesn't actually matter. The only thing in this thing that's called the main boot region, and this is the first 11 sectors of the disk, the only thing we care about is the first sector, and that is the main boot sector. That's the only thing that we care about for the purposes of this class. Immediately following the main boot region is the backup boot region, and it's literally a copy of the main boot region. It's just duplicated. After the backup boot region, so after we've got the main boot region and then the duplicate of the main boot region, after that we have the FAT. The FAT itself is where we have information about ultimately how to get our stuff back again. We will talk about how the FAT works in a second, but this is going to be a big array of 32-bit values, a big array of 4-byte values. That's what we'll know about this right now. It's a big array of 4-byte values. The closest synonym that we have for the FAT, the closest thing that we have, is part of an inode structure. It's part of the inode structure, and it's the inode number itself. That's the closest thing we have to represent the same idea of FAT entry here. Following the FAT region here, and this is N sectors, the FAT is still measured in sectors, and there might be more than one sector worth of bytes that represent the FAT. The number of sectors that the FAT takes up is something that we're going to be able to get from the main boot sector itself. After that first FAT is what's called the second FAT. It doesn't matter, it's irrelevant to us. The first FAT is the only one that we care about, and the file systems that we're working with will have one FAT that we care about. We don't have to worry about the second FAT at all. It's irrelevant to what we're thinking about here. After the second FAT is maybe some empty space. Maybe some empty space. And we also don't have to care about that because it's empty space. That's actually something that we don't really want to have in our file system. But it's here so that the data region, and this starts immediately after this possible empty space, but it does definitely start after where the FAT is. This is the data region of our file system. The data region now starts at an offset, so it starts somewhere in the disk that's specified by the main boot sector. We'll take a look at the main boot sector in a second to see how to figure out how to get to this thing. The data region in FAT file system is called the cluster heap. The data region in our VSFS and ext2 is called the data region. It's called the cluster heap here. They are synonyms. They mean the same thing. They are conceptually the same idea. The big difference is that when we're thinking about the cluster heap, we're using the word cluster as the base unit here, where we were thinking about blocks with VSFS and ext2. In VSFS and ext2, we said the block size is 4 kilobytes. Here, we're saying the cluster size is 4 kilobytes. They mean the same thing. They mean exactly the same thing. The big difference, the big thing that I want to point out here, and I will point this out again later, is that the cluster heap itself is not a 0-based array. The cluster heap itself is a 2-based array. Again, oh my God, again. I don't know why. I don't know why. The inode table is a 1-based array, and that sort of makes sense. Sort of makes sense. The cluster heap is a 2-based array, and it makes no sense at all. But this is the way that it is. This is the way that it is. So the first cluster in our cluster heap is cluster number 2. It's a 2-based array, and so the second entry is 3, the third entry is 4, the fourth entry is 5. I'm saying this now, and I'll say it again, because all the arithmetic that you're going to be doing to figure out how to get to a cluster has to be off by 2. It always has to be off by 2. The first cluster in the cluster heap is cluster number 2. This is the big structure. This is the overall big structure of this file system. So we've got main boot sector. That's one part that we actually really care about. A bunch of other stuff. And then we've got the FAT. And this is another structure that we care about. There's some other stuff. And then the cluster heap, the actual data and the actual directory entries for the thing that we're looking at right now. Are there any questions about this structure right now? This structure is not in the textbook. Yeah. It's, again, it's functionally very similar to the way that VSFX looks. And you can kind of take that structure of like, here's an array of blocks. This is the super block and the inode table and stuff like that. And you can kind of overlay it in this similar sort of structure. But this is for exFAT specifically. Yeah. Sure. So really quickly, and I'm glossing over a lot of things that we just don't care about because they're not actually important to what we're thinking about. The main boot sector here, this is functionally the same as the super block. It has metadata about our file system, and we're going to look at that right away. The extended boot sectors, OEM params, and boot checksum. These are all part of the main boot region itself. So they're things that are related to metadata about the file system, but it's not metadata that we actually care about. For us, we don't care about it. A person who's writing an actual file system driver might care about this stuff, but we don't. We don't really care much about that. The backup boot region is a duplicate. It's exactly the same thing. It's taking everything from the main boot region and it's just duplicating it here. It's identical. There might be some differences, but they're not really important. And again, we don't actually care about that. So the only thing that we care about from the beginning of this is right here at the beginning, and that's the main boot sector. The main boot sector itself is 512 bytes in size. It's fully 512 bytes in size, and that will have everything that we need that we care about. After that backup boot region is the FAT, the file allocation table, and this is a part that we actually care about here. This is something that we are going to use in just a second to try and get data out of our file system. Then there's the second FAT, which we don't care about, and then maybe some empty space, and then the actual contents of the file system. So this is our data region here, and this is where all the bytes of our files are going to be, and all the directory entries for our file system are going to be. Okay. All right, awesome. So I'm going to pop back to my web browser for a second. And what I want to do is I'm going to click here on section 3.1 because this starts to describe the structure of the main boot sector itself. The structure here is pretty similar to that table that we were seeing with ext2. It's telling us about the offset of each of the fields that we have here and their size in bytes. There's a bunch of stuff in here. And I'm only going to point at a couple of these things because in my mind, these are the only things that are important for us right now. I'll let you spend more time with this document later. But the file system name here, I'm going to click on the section 3.1.2. When we click on each of these fields, it tells us what this value actually is. And so file system name here, this one it's not the same thing as the file system label, like what we are passing with that uppercase L option. This is literally the characters uppercase exFAT space. That's what this is. It's always going to be this on an exFAT formatted file system. So if we want to check, is this an exFAT formatted file system, I should be able to seek to location 3, and then the next 8 bytes should be exFAT space, space, space. That's what that field is telling us right now. The must be 0 field is, well, it's literally 53 bytes of zeros. That's what this field is. It's just 53 bytes of zeros, and it has to be 0 because it's called must be 0. The volume length tells us how big this volume is measured in sectors. Some of these fields are measured in sectors, and some of them are measured in clusters. And so I'm going to go back to this, back to the table itself, and I'm going to go down here just a little bit here to the bytes per sector shift and sectors per cluster shift. These values are used to represent how many bytes are in a sector. The first sector is always 512 bytes. You can just assume that. This structure is 512 bytes in size. The bytes per sector shift is a field that you can use to shift 1 by to get the actual number of bytes in a single sector. So what I mean by that is the bytes per sector shift field will be something like, we'll use it something like this: 1 left shift bytes per sector shift. I'll show this again in a moment, but the idea here is it's going to say something like the bytes per sector shift is 8. That will shift 1 over 8 spaces, and that number that we get as an output from that will say this is how many bytes there are in a single sector. The other field that we care about is the sectors per cluster shift, and it's the same use of it. So we use 1 and then left shift it by that many spaces, and that tells us how many sectors there are in a cluster. So to figure out how many bytes are in a sector, we have to figure out how many bytes are. To figure out how many bytes are in a cluster, we have to figure out how many bytes there are in a sector, and then how many sectors are in a cluster. Multiply those things together, and we'll figure out how many bytes there are in a single cluster. The other thing that we have to care about here are things like the FAT offset. The FAT offset says that this is a volume relative sector offset. So this tells us how many sectors into the file system we need to scan to find the start of the FAT. And the other one that we care about is the cluster heap offset. The cluster heap offset is also a sector offset. So it tells us from the start of the file system, this is how many sectors we have to look before we get to that cluster heap. These are the main things that we really care about, but there's also a boot signature here close to the end, which is 2 bytes, and it's always AA55. So this is kind of like that EF53, I think, with ext2. There's a special magic value here that says this is a valid exFAT formatted file system. All right, so we'll come back to this maybe a little bit later. But the next thing that I want to do is I want to spend some time taking a little bit more of a look at the way that we're going to go through the process of like getting files and what files and directories look like in an exFAT formatted file system. So I'm going to scroll up here just a little bit, and I've started preparing this this worked example of what we're going to be looking at here. So in the top right side of the screen, I've got, this is the kind of like abstract directory structure that we're looking at right now. So we'll say that this is a Windows machine that we're working with, and we're going to say that this is a volume that has been mounted to the E drive. This, if we were to open up Windows Explorer and we see an E colon that represents this drive, this is the drive that we're currently looking at that is our exFAT formatted file system. The E drive, in the root of the E drive are 2 things. There's a file here that's called hello.txt, and then another directory. And then beneath this directory, there are two files, one that's called hi.txt and then another one that's called image.jpg. So this is what our file system looks like for us as someone that's taking a look at Windows Explorer right now. Some of the stuff that we're going to get from our file system is from our file system metadata from the main boot sector itself are things like what the first cluster of the root directory is and the cluster size is itself. So I've written this expression out for you. You are more than welcome to just like steal this. It's public knowledge. This isn't something that I'm worried about you taking, but figuring out how big a cluster is this expression right here. 1 left shift bytes per sector shift times 1 left shift sectors per cluster shift. This is just multiplying those two values together to figure out how big our cluster size is. The other things that we're getting from our file system metadata from our main boot sector are things like where the FAT is and where the cluster heap starts. To start with, the structures that we're going to be referring to here to begin with are kind of similar to the way that we were working with ext2. With ext2, in our super block, we had this is the, in the inode table itself, we had this is the first, this is the inode for the root directory. This is the inode that represents the root directory, and it was inode 2. We are coincidentally going to use the same number here to represent what the first cluster of our root directory is. The first cluster of our root directory is directory number 2. The way that we work with the FAT file systems is that we use this FAT to build up a structure that's called a cluster chain. A cluster chain is a linked list. It's a linked list. It's a really fancy way of saying this thing is a linked list structure. And so I'm going to zoom in just a little bit here. And what I'm going to do is I want to start building a cluster chain for the E drive. This is the root directory. So my cluster chain for E : /, this is my root directory. The first cluster of my root directory is 2. And so what that says is that the first node in my list is cluster number 2. That's the first node in the list that I have here. To find out what the next node in the list is, I need to look at the FAT. The place that I look in the FAT is entry number 2. The next node in this list is the value that's at entry number 2. So I'm going to take a look here at my FAT, and at entry number 2, the value that's here is 3. So what that says is that the next cluster in this chain is cluster number 3. So that's the next node in my list. Then I'm going to say, okay, well, if the next node in my list is number 3, I need to look at entry number 3 in the FAT. The value that's here is FFFF. And what this says is this is the end of the chain. This is the last thing. And we can sort of interpret this as saying that my list has ended, and I can say that there is no more nodes in this list structure. There are no more clusters in this list structure. So my first step is to open up my main boot sector, find the first cluster of my root directory, move to the FAT, and then start looking at entries in the FAT. I'm going to look at entries in the FAT, and I'm going to say that at the first cluster of root directory is 2. That's my first node. The value here is 3. So that's the next node in my list. I go to location number 3 in the FAT and I check to see what its value is. It's FFFFFF, and that says that this is the end of the cluster chain. There are no more nodes in this cluster chain. Once I have that information, now I can move to the cluster heap itself. The first cluster of the root directory is a directory. It's a directory. And so what that means is that we can immediately begin to interpret this cluster's data as directory entries. I'm going to come back here in just a second. I'm going to pop back over to my file system specification here. And I'm going back up to the top to the article, the table of contents. And I'm clicking on, this is section 7, directory entry definitions. There are a bunch of different directory entry definitions here. And I'm not going to talk about all of these because only 3 of them are really important to us right now. Only 3 of these different types of directory entries are important to us right now. The first one is called the file directory entry. Then there's the stream extension directory entry, and there's the file name directory entry. One piece of information that we get from this is that all directory entries are fixed in size. They are 32 bytes in size. They are always 32 bytes in size. They're always 32 bytes in size. And for a file in a directory, there's always at least 3 entries. I'm going to draw this out. The directory entry structure, and this is described in section 7.4, there's always at least 3 per file, where a file is like a file that's in this directory right now. So if I go back up here to my folder structure, in my root directory, I have 2 files, hello.txt and then directory. Those are the 2 things that I have in my root directory. So there's going to be 1 entry set for hello.txt, and there's going to be another entry set for directory. There's 2 entry sets here. Each entry set consists of at least 3 directory entries. There's going to be a file directory entry. There's exactly 1 of these. There's always exactly 1 of these. And this says a file is here. This is where a file is. There's a lot of metadata in this, but one of the main pieces of metadata that we care about is that we're going to be able to figure out what type of file this is. Whether it's a regular file, a file that has data in it, or it's a directory. The thing that comes after the file directory entry is the stream extension. And there will be exactly 1 of these stream extensions. The stream extension tells us things like, importantly, where the first cluster is, for the thing that we're looking at right now. So just like we know what the first cluster of our root directory is, every stream extension tells us this is the first cluster for this file. This is what we're going to use to go back up to the FAT to build another cluster chain for a file that's represented by this entry set. The last thing that's in an entry set for a file are the file name entries, and there's at least 1 of these. The file name entries, they're the name of the file. They're the actual name of the file in here. There might be more than 1. It's possible that there's more than 1 file name entry for a single file. Every file name entry contains up to 15 characters, 15 Unicode characters. If there's more than 15 characters in the name, then you have more than one file name entry for a file. So the structure of this, we go back to our cluster heap here, is that the first cluster of our root directory is at cluster 2. The cluster size that I have here is that this is 128 bytes per cluster. That's unrealistic. It's not actually real, but it's useful for us because what we can say is that there's exactly 4 directory entries per cluster if it's a directory. We can figure out at most how many directory entries there are going to be in a cluster by calculating how big a cluster is, and then knowing that each directory entry is only 32 bits in size. It's always only 32 bits in size. The way that this is going to look is that we're going to start by having a file directory entry. I've done a terrible thing, and I've made this not an even number of squares. So please forgive me for not putting things on the lines that are on the grid. Please forgive me for not putting things on the lines that are on the grid. This is going to be divided up into 4 different parts here because we're going to have 4 directory entries per cluster. The very first thing that we're going to see here is a file. And the file directory entry in this case is going to tell us that the type of this thing is a file. The folder structure that we're looking at right now is that the first entry in my root directory is hello.txt. So the entry set that we're currently building up here is going to be for this file hello.txt. That's the one that we're building up right now. The second thing that we're going to have here is a stream extension. Whoops. A stream extension. And the stream extension is going to tell us what the first cluster of this file is. And I'm going to say that the first cluster of this file is 4. This is a file, and the first cluster is 4. And what that means is that if we looked at cluster 4, it should be the contents of hello.txt. That's effectively what we're able to say from this. There's a stream extension, and then there's a file name. In this case, hello.txt is fewer than 15 characters, so this hello.txt would be entirely contained within this file name directory entry. What follows that now is a new directory entry structure, and it's for a new entry set. The new entry set that we have here is going to be for the directory entries for this directory. So the first 3 that we have here are for the file called hello.txt, and then immediately following that is another entry set for a new thing that's in this root directory, and that one is going to be for the directory itself. What we're going to find from this is that the file type itself is a directory, and then we're going to have some more entries in this cluster that's next to it. These 2 clusters that contain directory entries for the root directory are contiguous. They are physically next to each other, but that's not a strict requirement. And we're going to see this when we actually look at some real data, but when we're looking at examples here, we'll try to also see this. It's a coincidence that they're right next to each other. It's not a requirement. It might be that there's data in between directory entries that are even within the same entry set. But we'll keep going with this. So we've got a file. We've got a stream extension. And the stream extension for this folder says that the first cluster is at cluster 5. And then we're going to have a file name entry. The name directory is entirely contained within this directory entry because it's got fewer than 15 characters in it. And then what happens after this is that the rest of the entries here are going to have an entry type of 0x00, hexadecimal 00. One thing to note in the Microsoft documentation is that they'll represent hexadecimal values like this. So 00H means that it's 0 in hex. When I'm writing hexadecimal values, I tend to prefer using the 0x notation to represent it, but they mean the same thing. The H here says hex, and the X here also says hex to me. All right. So now we've got our directory entry sets for the root directory itself. We have 2 entry sets, one for each of the files that's contained within that root directory. And what I want to do now is I want to try to follow and build a cluster chain for the file itself, so that we can figure out how to get to this data. So the first cluster for our file is going to be this one right here. This is cluster number 4. So I want to build a cluster chain for the file that's called file.txt, or hello.txt, sorry. The first cluster for this is cluster 4. We know that from the stream extension itself. And when we look at entry 4, it's FFFF. And what that says is that there are no other clusters in this chain. So our cluster chain consists of a single node here. And that kind of implies that the whole data for this thing is contained within cluster 4. There are no other clusters for this. So our file here would have the data in it immediately, something like hello world. Would be entirely in this cluster. And just like blocks in our VSFS and ext2, that whole cluster would be allocated for this file, even though it only takes like 10 bytes or whatever. The entire cluster would be allocated to that thing. If I want to descend into the cluster for my directory, I would kind of do the same sort of overall approach as what I did for the root directory here. I'd build up the cluster chain for it. And then when I'm looking at the data in the cluster heap, I'd be able to interpret those as directory entries themselves. So I'm going to zoom out here just a little bit. And if I were to go now to try and find this directory contents, the contents for this directory, I'd follow the same general approach. So very quickly, I would do something like building up the cluster chain. By saying that the first cluster of this thing is cluster number 5. In my FAT, I look up at my FAT at entry number 5 and see that it has value 6. And if I look at entry 6, it's the end of cluster chain marker. So this chain consists of 2 clusters. The actual contents of this these clusters here are going to be directory entries. For that directory. So the same kind of structure as what we saw. There'll be entry sets for the 2 files, hi.txt and image.jpg. There'll be 2 sets of things for that. There'll be a file, and then a stream extension, and then a file name after that. All right. So this kind of takes us to the end of this visualization of our file system. I'm going to revisit this, I think, next class. I'm going to revisit this next class a little bit. What I am going to say is that I'm also going to be posting today assignment 1. I'm going to post this up on the course webpage today, and we'll spend time talking about this in class on Friday. So what that means is that we're going to be a little bit behind in terms of the content, and I'll try to make sure that when we're thinking about content that we're like moving stuff around in the schedule, and I'll let you know more about that on Friday, how things are going to be affected by that. All right, so that's it for today. I hope that you all have a good rest of your day, and I will see you on Friday. Bye, everyone.